I'm gonna show you a couple of ways that you can use the Go tracing tool to sort of inspect your program and maybe find things, I hate saying performance issues, but things we can find that maybe improve the performance of your software. So I'm gonna give you a little sample program, but it's kind of like a real world program. The idea is I got a function called frequency. It takes a topic, and then it takes a slice of documents, in our case, maybe a bunch of documents that are RSS news feeds. And the idea is that we want to see how many times this particular topic shows up in any given news feed. And this version of the algorithm is fairly simple. It's single threaded there, right? We're going to do a linear traversal across all the docs. We're going to open up that file. We're going to read the whole thing into memory. We'll unmarshal that into a Go struct. And then we'll just use string.contains, looking at the title or description. And every time we find that particular topic in there, we'll increment that found by 1, and then we'll return what that is. Now, I don't want to have a lot of documents here, so I've created this one news feed. It's way old. It's back from like 2017. And the idea is that we're going to start off with saying that we're going to have 4,000 of these. So let's just pretend there's 4,000 unique documents. Ideally, I want to be able to process millions of documents, but for now, let's just say we're going to deal with 4,000. All right, so I can go ahead and I can build this program, and I can even use my little time program to get a basic sort of wall clock. And if I run this, I'm going to run everything twice because warm the machine up a little bit. So if I run this right now, it looks like that out of those 4,000 files, we found that topic. I think the topic was president. We found it 28,000 times, and it took a little over a second for that to happen. Now, if we were only going to process 4,000 files, I'd say we're done. I mean, that's fast enough, okay? But let's say we've decided that that isn't fast enough. We've got to figure out what is potentially slowing this thing down. Now, we could do a CPU profile, and if I had time and I did that, we would basically see in that profile that what's sort of slowing us down are system calls going on in here. And at the end of the day, unless I can buy a much bigger machine, right, the system calls are what's there. So profiling is really cool, and we did some profiling yesterday, but I think one of the problems with profiling is it can only show you what's happening. And sometimes your problem isn't based on what's happening, it's based on what's not happening. And this is where the trace tool comes in, because the trace tool can also show us, in many cases, what's not happening in the program. Now, I've got a program that runs fairly quickly. So what's pretty cool is that the standard library has this trace package in part of the runtime. And I can use the trace package to start a trace. So I'll send it to standard out, and then we can stop it. But you can get traces running benchmarks, running tests. You have all these options to sort of generate. Now, the trace data is down to like the microsecond, produces a lot of data. So you really want to be very targeted when we're running this. This is a beautiful program. It's running like a second, right? So it's perfect. So let me turn that on. Let me go here and we'll build it again. And this time when we run it, we'll do the time again, and I'm gonna send everything to t.out because that's where we're putting it. And again, I'm gonna run it twice. And now I have a t.out that's about 1.3 meg. I mean, that thing ran for a second, and I already got a meg of sort of data there. All right, let's get a sense of, let's take a look at the trace. So I can go to Go Tool, Trace, t.out, and we'll bring up the browser. I'll make this a little bigger as we go. And over the years, they've added a lot of cool stuff in here. Maybe somebody one day will give a talk on more than this first link, which is what I'm gonna press, which is gonna show us that trace data at the proc level. So I have a machine here that's got 16 cores, so I'll have 16 procs. And you can see a little bit here what's going on, but I'm gonna expand this just a tiny bit. So I'm gonna even see if I can make it a little bit bigger for you, and I can expand some stuff here. All right. So real quick, you can see the top line is showing you how many goroutines at any given really microsecond, but we're in the milliseconds there. We can see our heap graphs. We can see operating system threads. We can see GC. You can see pacing. And then you can see goroutines that are executing across the different procs. In fact, I told you I've got 16 procs and really only 7 of them are showing up. What's also cool is if it's important to you, you can sort of click on these goroutines. You can see a stack trace of what was happening at that time on that given goroutine. There's a lot of stuff there. But remember, this talk is about, is there something in this trace that's going to help us sort of identify why this program isn't running as fast as it otherwise could be? And if you just look at this view alone, I think it ends up being fairly obvious. This program is only using 1 core of the 16 that I have at any given time. Look at the green lines, the G1. There's only 1 goroutine, number 1. And even though during garbage collections, every time you see one of these lines here, we've got a garbage collection, we might be bouncing across different Ps, it's still at the end of the day single-threaded. The only thing that's using more CPU is the garbage collector. In fact, if we were to, let's just say, expand this particular garbage collection here, you would see the initial stop the world. You could see here that we're doing some concurrent work phase, another stop the world over there. You might even see that we're in mark assist, which means we're also helping the garbage collector at that point. And we could see sort of what's happening there. But I think the bottom line is what this is showing us, at least right now, is that if we really want to run faster, then we should really try to turn this program into a concurrent program. Now, when I say concurrency, what do I mean? The best definition I've ever heard for concurrency is out of order execution. I love that idea. Out of order execution. Given a set of things you have to do, no matter what the order is, as long as you get them all done, everything's going to be fine. In fact, we have that situation here. I've got 4,000 files that I need to process. In all reality, it doesn't matter what order I process them in. As long as I get all of them done, we're going to get that same result. This is a perfect opportunity for concurrency. Now, I did tell you I want to be able to process millions of files, but let's slow down a little bit. Let's just focus on 4,000. And what will be the easiest way to turn this program into a concurrent program? Well, as a first step, what would be interesting is just throwing 4,000 goroutines at it. Let's just do that. Let's get there. We know we really can't settle there, so I'm not going to throw 1,000,000 goroutines. I will run out of file handles at some level before that. But it's a good first sort of step. So how do we take this program and get it so now it's going to be concurrent? Well, we've already decided that what we're going to do is identify that we're going to want to use that number of goroutines. So whatever the size of that slice of documents is, that's what we'll do. Now we've got an orchestration problem. We don't want this function to return until everything's been done. And so what we'll do then is use a wait group. And the wait group will allow us to do this orchestration, where this main goroutine will wait on the other 4,000. So we'll do our add call. We know how many we want there, G. And I can come all the way down here by the return and say, okay, we're going to wait for all that to finish. And now we've already doing the linear traversal. That's fine. We have a document. What we kind of want to do here now is sort of wrap this around a goroutine. It's nice that we've got the 4 sort of steps isolated. Now we're not going to return anything from here. That's fine for what we're doing. And now what's really cool, actually, on some of the new features of Go, I think this was in the last release, but I don't remember. This range now gives us a guarantee that this doc variable will be unique. In past versions of Go, that wasn't the case. In past versions of Go, we would have had to probably do this to make sure that each goroutine had a unique document, right? But how beautiful is this? We don't have to worry about that now. You don't see any linter issues related to that either. Now, I'm about to forget the one thing that we always forget to do when we're working with wait groups, right? When this thing is done, we've got to call done. Now, in Go 1.5, they've now added to the wait group this go function. And that will eliminate you forgetting to call done. Now, if you just bear with the old man, the done API call and I have a long history together. And so I will retire it after this talk. Is that fair? Okay, thank you. So we're going to use done one last time. This might be the last time done is ever used. Moving forward. Okay, now you might think, Bill, you've done it. You've got all of this orchestration in place now. We're going to get 4,000 goroutines. We're going to wait. We're going to get the count. But let me do something first. Let me make sure that life is good. Let me build this program with the race detector. Maybe I missed something. Now, a data race is when you have two or more goroutines trying to access the same memory location at the same time, where at least one of those goroutines is doing a write. We don't want multiple goroutines accessing that shared memory where there's mutation going on. We're going to, at some level, get corruption. The race detector is going to find that. So if I do this now, and I just say, run this with the race detector, it didn't take too long, did it? There it is. I absolutely have a data race. And now what I'm looking for is the word previous write. It's going to be in there somewhere. And so what it's telling me is the goroutine here had a previous write on line 94 and actually found it a couple of times. And so if we head over to that code, not surprising. So this variable, this local variable to the function before was fine because we had one goroutine, but now we've got up to 16 goroutines running in parallel, and this local variable now has kind of become a global variable. So we can't have that. We've got to fix this data race. Now there's a couple ways that we can do that. We're going to use the atomic package though, because this is just a word of data, and we can get this at the hardware level, which is the fastest way. The atomic package gives us two choices. The choice that I'm going to choose is to use the function called add int 32. You could do it at a 64 as well. That will take the address of that variable found, and the delta will be just 1. We can do that in both cases. Now it's complaining because found isn't a 32-bit int, it's just specified as an int. So if I make that a precision-based integer and I do this, it will go away. Now, you have another choice here if you really want to. The atomic package has a value, which then has a method set. And that might be easier for you because it sort of hides some of those 32-bit, 64-bit sort of details. But I'm going to stick with this. Now, that should get rid of the data race, right? So let's build this again. We can run it again. And I didn't put time in front of it. We'll do that in a second, but no more data race. Now there's actually another little hidden gem here that isn't obvious, and we won't really see it on this program with 16 cores and 4,000 files. But we're also very much thrashing memory here. You see, this variable called found, what's going to happen is every one of these goroutines that are running on a core will have to pull a copy of this into that processor. It's going to copy that into one of the L caches. And so what's going to happen to us, we won't see it here. You might think this program's great. You put it in production on a very large machine and you're trying to figure out why is the performance not scaling. Every time we run this now, what's going to happen is that that core is going to have to do the operation and then tell all the other cores, your copy is no longer valid. So when the next goroutine goes to do the plus, we're going to have to now wait to pull a new version of that into and do it again. We're essentially going to be thrashing memory. We're not going to see it on this little program, but it's happening. We really don't want that to happen. And we already know it's going to happen 28,000 times over the 4,000 files. So when you have situations like this, another thing that we can do is just say, hey, every goroutine has a stack. Those stacks are starting out as 2K. So any local variable on the stack, there's no way that that's going to fall within the same sort of cache line. We can get around that by doing this. So I don't want to be incrementing these counts here. I want to use a local variable. Now, we still got to put this back, right? So maybe what I'll do here is I'll just get a literal function here for my defer. I can do this and say at the end, let's just whatever lfound is, we'll write that back. So now it's not going to be 28,000 times. Now it'll be 4,000 times. There's more improvements we can make there. But now what's pretty cool is I can just do this. This is the bulk of what's happening. So now I got a local variable doing the counting here, and then when we're done, we'll go back, we'll take the little hit. It's still not perfect, but it's better. And now we've got a concurrent program here that should run faster. All right, let's go ahead and build this. Let's go back and use the command we have with the time, just giving us a basic wall clock here. I'm gonna run it twice. Okay, we're already down to 289. Now let me bring this up, and then I'm going to bring some stats up on the screen as well. Go to trace, Bill, t.out. So let's do the following. I'm going to come back to the very first trace to begin with. Let me come back here for a second, because I really want to understand as we make improvements, how this is going. So I'm going to do the following here. The original program that we ran, let me sort of mark how fast. So let's just say, let me open up a text editor here again. Let's just say the following, at least for this program here. So the total time that this one ran was like 1,000 milliseconds. This is the very first program, which is that sort of single, all right? Now, what other information should we be looking at here? Well, one of the things we could look at is on this heap, like what was sort of, and there's better ways to do this, but what is sort of where the memory's at? Look at this heap graph, by the way. Look how nice and straight it is. Look how clean it is. Look at the pacing is beautiful. We love to see this stuff, but I'm kind of curious what's going on here. You're going to see green and orange lines here. The orange line is how much memory is live in the heap. And that green is basically the target value. If you look at the very first garbage collection, the GC will kick in once you've got 4 meg of memory live in the heap. That's what we're seeing there. And then you see that the garbage collector has started to make a decision that it thinks like 5, almost 6 meg of memory is a good sort of spot to sort of stay at. You see that consistency. So maybe what we could say here is that like that max sort of memory that we have right now, maybe it's like 6 meg. All right, we'll just kind of use that number. It looks very consistent. Now, another kind of cool thing to look at for us is what's going on with garbage collection. Every one of these lines is a garbage collection that took place. If I double click on that, I get information about all the GC that happened. So I know that there were 408 garbage collections that took place, right? There were 408 of these that happened. All right, cool. And I know that it was nanoseconds, microseconds, milliseconds. I know that, right, the total wall time or duration here was 68 milliseconds. Now that's kind of cool because if we just do a tiny bit of math here, right, divided by that 1,000 milliseconds, we see that basically the percent of time that we're in GC, I'm going to round that up. It's about 7%. That's kind of cool. So just looking at these numbers alone, we know that our first algorithm, okay, we know how long it took, we know how many garbage collections that was there, we know how we're kind of where we peaked in memory, and we know that we were running GC about 7% of the time. But look at the new version, our concurrent version. Look at this. I got every single proc going. It's super dense, faster. But look at the heap graph. Heap graph is all over the place, man, right? Look at the Goroutines. This is cool. Every time I run this, I see the scheduler do different things. Look at here. I can click on here and we could see how many of those 4,000 Goroutines, what state are they in? See, they started out slow and then it went bah, and then it started going out and went bah, but whatever, that's not going to help me here. The heap graph is super interesting though. That's what I want to focus on. So let's just do the following. Let's just get some numbers again from this algorithm here. So we're at like 264 milliseconds, right? This is sort of our fan out. We can call it that. So we're at like 264 milliseconds on that. Okay. Nice improvement. Now, what about some of the memory issues here? I don't know. I'm just going to like look for the biggest peak here. And it looks like 55 meg at that point. It's about how much memory we're sort of at. I think that's a good number. So let's just say that. We went from a max of about 6 to 55. It's still small, but it's kind of cool to see what the garbage collector sort of did with this particular load. Now, what about the number of GCs that took place? That's going to be interesting. All right. So what do we got? We actually go down to 92 garbage collections at 172 milliseconds, which, if we start doing a little math on that, okay, we have a faster program. That's for sure. These are the new numbers. But we are running garbage collection about again, wall clock stuff, but like 65% of the time this program's running, there's some garbage collection sort of going on. But it's still faster than sort of where we were, and I'm using the full breadth of the machine. This is pretty impressive. However, this is fine if you're going to do 4,000, but I want to get to 1 million. So throwing 1 million goroutines at the problem isn't really going to help. What we need to do is control the number of goroutines and control the work. So why don't we do this? Why don't we change the program, and we'll change it so we're executing all this work on a pool of goroutines, where we're feeding it. And let's just see what the sort of dynamics are when we make that change. Okay, so how many goroutines should be in the pool? At this point, my recommendation would be, let's create a goroutine for every core that we have in the system. That's a pretty good place to start. You don't want it to be random. This is a good place to start. We still have some of that synchronization that goes on, but now we're not doing a linear traversal like this. We could actually leverage another new syntax choice and go and do this. This is really what we want. We want to create G number of goroutines. So we can do that. But now that causes a problem, because how are we going to feed any one of these goroutines work? That's an orchestration problem. So now what we can do is come in and we'll make a channel of type string, and let's make it a buffer of G2. That way we're sort of posting up the next work for any given G without really like burning too much memory there. But with that channel now, what we'll do is we'll tell these goroutines that you're going to block now on this channel, which is going to be a channel receive. And then when you get chosen to do the next piece of work, that for loop will iterate and you'll get your document. The only thing we haven't done now is start to feed it. So here we'll do the linear traversal. We'll pass that document into the channel. And once the very last document has been sent, we'll close the channel and wait. At some point, every one of those 16 goroutines will go back to the for loop. It will see the channel's now closed because there's no more work and everything should sort of shut down. Okay. So we've just moved this from a pool, from like a fan out now to a pool. I would think that this is now going to be more efficient, because if you think about it, now all of the counting is happening on the local variable. We're only doing this now 16 times. That's pretty cool, right? We're even getting more mechanical sympathy related to how the caching system works. So I think we all expect this program to run faster. Let's see what happens. Well, I'm going to build it again. Here we go. And I'm going to run this twice. We actually got slower. Interesting. All right. We don't guess and go. We look. So let's do a trace. Let's take a look at this program. And let's see if we can figure out what's going on. So we're definitely using the full breadth of the machine. But look at the heap graph again. In fact, look at this. That's super interesting. The garbage collection seems to be working overtime. Let's see if we can kind of get a general sense of what's happening here. Let's open this up a little bit. If I kind of look at the heap graph here, that's 13 meg, all right? Maybe we've got some more peaks, 12, 13. So it looks like in this scenario where we're limiting the number of go routines, the garbage collector decided, and as it wants to, we want to minimize the amount of memory we're using, it was able to keep the heap at about 13 meg. However, to do that, it really had to pace pretty hard. Let's actually take the numbers here and compare them with what we have on that other sheet. So our total runtime was 388. All right, not a problem. This is our pool. So we had, 388 milliseconds, sweet. We already said that our max here was like 13 MIB, okay. So memory came down, no problem, that's good. What about the number of GCs? I'm actually afraid to ask. Let's open this up a little bit. All right, 349 garbage collections. Now, you might think like, yeah, that was a lot, but it's still less than what we had before. And the average duration was 289. I'll just use 289. Okay. And then if we do the math on this one, we had 289, and we're going to divide it by our 388, and we're going to get a big number like 74%. Okay. So we're actually spending more time in GC, still faster than the single, but slower than the fan out. And we could argue that it's because Go is trying to be, and I think rightly so, very efficient with the memory. What's brilliant to me just about this alone is the majority of us who are building web services, right? Where we've got 10,000, 20,000, 30,000 Go routines in flight at any given time handling requests. Look how beautiful the garbage collector and the scheduler is. Just look at the fan out sort of pattern there. Look how beautiful that is. It's really gotten to a point where it's really well tuned for that sort of scenario where we don't want you to think about, just throw Go routines at the problem. Now, that's still not acceptable and it should be faster, but let's think about this. How could we make that faster? If we gave the algorithm more memory to work with, maybe that 55 meg, and not lock it into the 13, that would be pretty cool. I think we could get it faster. Now, there's two ways to do that. Remember when I said to you that the very first GC, if you don't do anything with any of the knobs, will start at 4 meg. There is a knob called the GC percentage, or on the command line, it's GOGC. Now, this knob, the default is 100. Which for our purpose with this talk means the first garbage collection is going to happen at 4 meg. What if, just for now, I set that to 1,000? I don't have to change any code here. But if I change it to 1,000, then the first garbage collection should start at 40 meg. Let's see what happens. Oh. We're already faster. Look at that. Let's take a look at that graph. That one's exciting. Oh, I like that. All right, let's just quickly grab some numbers here. All right, so what are we now at? We're 136. I ain't gonna cheat there. 136, right? So here we're using GOGC 1000. We're now at 136 milliseconds. Our maximum heap should be around what we talked about now. Let's see. I said it that way. What was the first GC? That one's interesting. Not a shocker, about 40 meg. And we basically maintain a 66, 70. So we go from like 40, but we sort of level out at 70, a little higher than what what everything was, the GC and the scheduler kind of working together in the fan-out pattern. How many garbage collections, though? Nice, 19. Look at that. Went down to 19 garbage collections with 18 milliseconds of wall clock here. And if we do that math, 18 divided by 136, give me a good number there. That's 13%. That's pretty good. All we did was tell the algorithm to use a little bit more memory, and all of this overpacing sort of went away. It kind of shows you, right? Sometimes all you need to do is give your program a little bit more memory, and then that will allow the garbage collector to relax. Oh, thank God. Oh my God. I didn't really want to keep it at 13, dude, but that's where I was at. Now, I find doing it this way a tiny bit scary. I just, right? That number, 40 meg, there's a better way. I don't remember what release of Go a couple years ago. The team added a second knob. Now, that knob is the GOMEMLIMIT. And you could set a number. Now, maybe what we'll do is I'm going to go back to this number here. That was like 55. I'm going to tell it, and I'm going to do something else, which I think is kind of cool. I'm going to turn off the garbage collector in the traditional sense, and I'm now going to tell the runtime, basically, there's 60 meg there for you to use. Use it. I don't care about bouncing up and down. Use it. Okay, let's see what happens. Guess what? It's virtually the same exact performance. But now it's not me arbitrarily saying, start the first GC at 40. It's me saying, I want you to work within the confines of this particular amount of memory. Now, watch what's super interesting, because we told it that there was 60 megs there to work with, right? So you no longer see green lines anywhere, because I've taken that off of the table. Now it's a matter of, we got to a certain memory size, in this case, 40 meg. You might be asking, why is it not using the full 60? This is going to be a much better question for the Go team, but I remember in a talk from Russ saying that the runtime also needs some of this memory. And so you gotta have, I don't remember if the number was 15 or 20% sort of margin there to make sure that the Go runtime has some memory to work with. So my guess, and again, it's a better question to ask the Go team later, my guess is that it's using 40, it's saving some of that memory for the runtime, but we're getting the same performance anyway, aren't we? That's really cool. And if we look at the number of GCs, was 32, and the number of GCs went up, but the wall duration is at 33, the size. Like, it's all basically evening out. Now, this is the coolest thing, I think. I do have garbage collection going on, do I not? We know right now that from our wall clock perspective, this is running at about 160 milliseconds. I can do this with this program. But if I completely turn off the garbage collector, I would argue that with the garbage collector on, with that amount of memory, and with it off, we're running at the same speed. For me, it's almost like the garbage collector isn't even there. How beautiful is that, man? It's out of your way. You don't even have to think about it. And when you're running Go programs where you're doing anything over the network, waiting for databases, talking to an LLM that takes a minute to come back, even the garbage collector is bored. You don't have to worry about this stuff. However, I think the interesting thing was this. I tried to make the algorithm more efficient. I tried to control the number of Go routines. I tried to pool that. And the garbage collector and the runtime took advantage of that to keep the memory low. But reality is that even the performance of all of these algorithms, they're all fast enough. And so throwing Go routines at a problem is an amazing first step. Do that until you can't. Don't try to control the concurrency. Throw it at the runtime. Throw it at the scheduler. Make it work. Make all the work that the Go team has done for the last 15 years count. Because it's amazing what they've done. I am out of time. Thanks, everyone.